Welcome, everyone. Glad you could join us today. I'll give a minute just for everyone to get logged in. All right. Again, welcome everyone to Heat Pump Water Heaters for Restaurants 101 and 102. My name is Susan Harris, and I'm the Building Innovation Communications Manager for New Buildings Institute, and I'll be your moderator today. Shannon Wilson is also on hand to provide support, and we have a panel of experts here with us today to talk about heat pump water heaters in commercial kitchens. They include Richard Young, Director of Frontier Energy, and Amin Delagah from TRC, the Principal Engineer of Research and Consulting. And we have Noah Gabriel, Project Manager, Building Innovation with New Buildings Institute. And we also have Tina Hendricks with us from CETA. Thank all of you for being with us today. Just a few housekeeping items. Please put any comments or conversation that you have for other attendees in the chat section, and then any questions you have for our panelists in the Q&A section. And if time allows, then we'll answer those questions near the end of our first part to our session. The links to the event recording and the slides will be emailed to you after the event. After our first hour and a half together, we'll have a little break. So at that time, please feel free to stretch your legs, grab something to eat, get some water, and then come back, because at 1 o'clock, we'll have the second part to our session when we'll have an installer and manufacturers on hand to talk to us more about commercial heat pump water heaters in kitchens and restaurants. And we'll about heat pump water heaters. We have ready-made posts for you to use on social media platforms of your choice. I'll put links in the chat. There's also the QR code. We've made it easy for you. You can grab these cool images and some examples of text that you could post. You're also welcome to make your own. We have a market transformation badge available for adding your own picture and your own task force and mission in this work of heat pump water heaters. This is me in front of a commercial heat pump water heater in the PAE building in Portland, Oregon. It's pretty cool. You can see the full program for preliminary events as well as Heat Pump Water Heater Day on our website. Again, we have a QR code here. I'll be putting links in the chat. I hope you check it out. We have a lot of leading thinkers with us talking about this important part of energy efficiency and decarbonization in the built environment. Also, if you post on social media, please include the tag hashtag HPWH Day or hashtag GoGo Heat Pump Water Heater, HPWH, so that we can find your posts. And then at the end of Heat Pump Water Heater Day on Thursday, there'll be a drawing, and some lucky person is going to win a free heat pump water heater. There's been a generous donation from Bosch and Ariston for heat pump water heaters that will be installed in the location of your choice. So good luck. We want to say a special thank you to our supporters, which include the California Energy Design Assistants, and I have Tina Hendricks here to talk with us a little bit about CETA.
Thank you, Susan. Just want to say thanks everyone for taking time today to join us. Want to tell you a little bit more about CETA and our role in California's goal to reach 6 million heat pumps by 2030. So today it's estimated that only about 1.9 million heat pumps are installed, and at that current rate, we'll only reach about 3.4 million by 2030, and that's going to leave us well short of the goal of 6 million heat pumps by 2030. So that's where the California Energy Design Assistance CETA program comes in. We're the only statewide utility incentive program for new construction and major renovation. And our mission is really to support the adoption of decarbonization measures such as heat pumps. And we're also out educating the market about available decarbonization opportunities. Why would you want to participate in CETA? First and foremost, it's completely complimentary, does not cost to participate in the program. And we offer a custom decarbonization analysis that's tailored to each project. We're going to help identify and evaluate different opportunities in things like lighting, HVAC, building envelope. It'll help gain an analysis of the energy cost as well as paybacks. And you'll also receive financial incentives and inducements to help offset the cost of some of those decarbonization measures for qualified projects. And last but not least, it's really demonstrating a commitment to high performance building practices and design. And you'll see off to the right, there is a $4,000 design team incentive for the design team. I just wanted to mention that as well. Heat pump measures, from standard heat pump measures to high performance systems, CETA really provides incentives that support decarbonization opportunities. You'll see a partial list here of some of our high performance measures. You'll see space heating systems, you'll see surface water heating, plug loads, process loads. And again, under our CETA program, we can include those measures. We also have a new online CETA screening tool. So if you're interested in finding out an estimate for the potential incentive on your project, you would simply put in some basic information such as project location, project type, project design stage, building purpose, and the square footage, and it will give you an estimated incentive amount, which is great if you're looking to learn that ahead of time. And you'll see on the right here, this is what the report comes out like. It'll show you the annual energy cost savings. It'll show you the projected incentive, and then it'll also show you the amount of trees planted in terms of carbon savings. Also wanted to mention that CETA does have a national presence, or Willdan actually does have a national presence with energy design assistance across the country. In addition to California, we work with the blue highlighted states here with many different utility programs to implement energy design assistance. So if you have projects that are outside of California in any of the blue colored states on the map, we may be able to help you with energy design assistance there as well. I'm Tina Hendricks. I'm the Program Outreach Manager for the CETA program. If you have any questions or if I could ever assist in any way, my contact information is on the screen. And there's also a link to our website, californiaeda.com, where we have some great information about the CETA program, case studies, just a world of information on there for you. So thanks so much for your time today and appreciate it very much.
Thank you, Tina. Really appreciate the work that you're doing out there.
Thanks.
And with that, I would like to pass the microphone over to Richard.
Okay.
Richard, if you would please get us started and share your slides.
Okay. And Susan, you have to stop sharing before I can start sharing. There we go. Okay. Now let's do it. Screen one and share. And I'm hoping everybody's seeing everything perfectly. Well, Tina, I have done my part for your 6 million heat pump water heaters. I have one in my house. I quite love it. So I'm helping out there. I'm glad to know about CETA. I think CETA is awesome. So let's leap right in. My goal today is to be the opener for Amin Delagah. I am the opening act. I'm going to give you some of the basics, some refreshers. I'm going to talk about what you can do right now today to actually get more of those heat pump water heaters into commercial food service. And then Amin's going to go deeper into some of the details, the technical stuff that we're learning, and where we're going next and how we're going to overcome some of the immediate challenges. So how about we leap right in? And I'll introduce myself first. I'm Richard Young. I am a director at the Food Service Tech Center, the Frontier Energy Food Service Tech Center. I've been there like 37 years, and every day I get up and I learn something new. It's a very exciting field to be in, and I'm thrilled. I'm going to learn stuff from Amin today. And just a fun fact, Amin and I used to be office mates, and so we think a lot alike. We're similar guys. I do always like to start with a safety message. I actually rode my bike dressed like this person. Let's get my magic pen going. Down this very street this morning to get to our WeWork space in downtown Oakland. Um, and all the way down that street, my biggest fear is that somebody's going to sling the door open and door me on my bicycle. And so what I'm going to ask you on behalf of all the bicycle riders out there is to do a thing we call a Dutch reach, which simply means that you use your right hand to open the door, which forces you to look back and keep an eye out for that bicyclist versus having your phone in your hand and just throwing the door open. Okay, so help me to get to work and home safely, and all the other bicyclists. And we really appreciate you for doing that. Quick disclaimer, everything I'm telling you today is the latest information we have to the best of our knowledge, but don't go hanging us on any little detail because, things can change. I have no liability for telling you this stuff today. I'm only going to tell you the truth. Now, I've got your time for a little bit, so I want to give you something back. In addition to the skill that I want to teach you today, which is how to apply heat pump water heaters in commercial food service right now, working with your environmental health departments, I also want to give you some resources that you're going to use to make all of this happen. And you may be saying, oh, Richard, okay, should I pay attention to this? At some point, somebody's going to walk up with a project tomorrow, and you're going to say, wow, what was it that Richard said in that webinar? And you're going to go back to these documents, and this is going to help you out. Special shout out to Barry Hooper and Nick and Nee and all the folks with City of San Francisco Department of Environment that have worked on the first and probably one of the most important resources, which is the technical bulletin. And so this is our technical bulletin right here. There's a link for it. Susan's also got this set up for you guys so you can get to these resources easily. And what this technical bulletin does is it allows us to use the second resource, which is the California Environmental Health Sizing Guidelines for water heaters, to actually implement a heat pump water heater in certain commercial food service applications right now today. So very, very valuable information. Like I say, hats off to SF people. This has been a labor of love for a while. Other resource, which is near and dear to my heart, is the California Energy Wise program. And a resource for you, starting with a bunch of seminars, including one that will be happening down at SoCal Edison next week. It will be a little bit longer, and we'll go into some more of these details. And if you have to turn off early today or anything like that, come to our class in Irwindale next week and meet us face to face and talk about this good stuff. Those food or equipment is equally important. We have try before you buy programs and centers in California. We can also send people out to help you with new projects and to do energy surveys. And then there's a whole instant rebates program as well that covers cooking, refrigeration, all kinds of equipment, kitchen ventilation, all this good stuff. So huge resources. But the one that is most important today is our California Energy Wise design guides. And these have been growing and evolving over the years. If you're doing anything with environmental health people, you're not just going to be working on sanitation, you'll also be working on commercial kitchen ventilation. So there's 8 guides out there. But of course, the ones most important to today's is these 3 guides on hot water systems, right? And specifically one, I'm going to mention it once and Amin's going to mention it again. And Amin actually worked with our team on this. the technical design guide for advanced water heating within the food service industry. This is golden, okay? Lots of what we're going to talk about today is in this design guide. It's simple to read. It's nice graphics, and it's got a lot of takeaways and a lot of guidance for anybody who is working in this area of hot water. We only have an hour and a half with you today, so we're just gonna touch on some of this stuff. But the design guide discusses strategies to implement an advanced commercial food service hot water system. So I think this is a great starting point right at the beginning. You know, we can't just take a heat pump water heater and just shove it into our traditional plumbing system and say goodbye. In the sense that a heat pump water heater is a different kind of way of creating hot water. We also need to look at the entire system as we put this new water heater in. And so as we talk about this, and once again, Amin will talk more, this is a systemic approach. The water heater is part of it, but all the piping and also how you design the system is important. So, and absolutely 100%, these systems have to meet all the hot water and sanitation needs. There can be no cheating on your hot water in commercial food service. If the system is not functional or cannot produce meet the sanitation needs, then the restaurant gets shut down. So absolutely important that we understand these guidelines. And then of course, second big chunk of all of this is we want to make this hot water and provide safe sanitation in the most efficient way and with the best performance. I want to turn on the water and feel that hot water as fast as possible, right? And you may say, oh, well, what the heck? In the cook line, the big deal? Hot water systems can account for as much as half of a commercial food service facility's energy. And as well as most of its water use. You would think, you know, oh, it's half hot, half cold. No, most of the stuff you're doing in a food service world is hot water. So water heating systems and designs, getting it right is super duper important. So let's step back now. What I'm going to do, and there are, let's see how many people are on the line. We got 112 engineering nerds out there. Thank you very much, energy efficiency people. So for some of you, this is going to be like 101 stuff. Others of you, this will be a great refresher. Every time I go through these slides, it always just kind of sets up the discussion, and this will lead right into all the cool things Amin has. So let's just define stuff, starting with what is an electric resistance water heater. And these are the traditional electric water heaters you find in any restaurant that typically doesn't have a gas water heater. It's a resistor chunk of metal that sits inside the water. I put some electricity into that. It heats up. It generates heat, which then flows into the water. So very, very simple water heating system, right? The challenge is that trying to put an electric resistance water heater into the hot water intensive commercial food service kitchen can be very, very costly. Okay, if you pulled out your gas tank and you threw in just a big resistance water heating tank, that could be 3 to 5 times the cost. And we don't want to do that to our commercial food service folks, right? So that's the big challenge with going with that, basics situation. The one benefit though is that right now today, if you were trying to do an all-electric restaurant and you went to your environmental health folks and said, I want to put in a resistance electric water heater, there is a pathway for approval of that standard electric resistance water heater because they have been around for a while and the environmental health folks are used to them. There's a method for that. What's a heat pump water heater? A heat pump water heater is basically capturing heat from the air and transferring it to the water in the tank. It's a different way of generating heat in that tank. And the heat pump is rated in kW, just like the resistance electric tank is, but it's based on the size of the compressor and not the size of the elements, okay? And this is a pure heat pump water heater tank. And the challenge with this is there is nothing in the current environmental health guidelines, the CCDEH guidelines, which addresses sizing a water heater based on the compressor. Okay, right now it's either flames, BTU for your gas, or it is resistance elements. So this is a challenge, right? And let's just talk about heat pumps really quick here. And just to get it in the mind for those folks who are not really familiar with how it works. So if you imagine, you have refrigeration, the product of a refrigerator is cold, it's air with the heat removed, and the waste off of refrigeration is heat, right? If you've ever been to a motel and you've walked into the little alcove where the ice machine is and you're pulling the cold ice out and you're feeling all that heat coming off the ice machine, that's what you got. The product is cold, the waste is heat. All you got to do is flip that around for your heat pump. Now the product is heat, okay, and the waste is cold. So I'm pulling heat out of the air, and what's left, the byproduct of my heat pump is air that's colder. So it's a simple concept. We're just taking refrigeration and flipping it upside down, and once again, using a compressor to make all of this stuff happen. So now let's talk about efficiency for just a moment. If I put 1 unit of energy into my resistance element water heater, I'm really getting 1 unit of energy into the water. So when you talk about that from an efficiency standpoint, an electric resistance water heater is really very efficient. I don't have a lot of waste heat going anywhere. It's all going right in. But I am converting energy. I'm taking electrons, electricity, forcing it through this piece of metal, which heats up, and then the heat comes off that metal. So keep that in mind. I'm converting energy when I'm working with an electric resistance water heater, but it's very, it's highly efficient, right? Now with the heat pump water heater, it's different. I'm not converting energy. I'm essentially moving heat and using physics to get some extra benefit out of that. And we refer to that as a coefficient of performance. So I can put 1 unit of energy into the compressor, but I end up with 1.5 to 4 times that amount of energy actually making it into the water that I need to heating my water. And once again, this is a refrigeration terminology, coefficient of performance, right? It's physics. Now, the thing about my heat pump water heater is it's going to be slower than my resistance heater, but it is very cost effective because once again, I'm simply moving heat back and forth. But you have to keep that in mind when we start talking about performance. Now, what's a hybrid heat pump water heater? Well, I'm taking my electric resistance and I'm taking my pure heat pump and I'm combining the two together, okay? So I have my heat pump, but I also have resistance elements as a backup. So that helps me with that speed issue. If I need I've drawn a bunch of hot water, I need a bigger hammer, I've got those resistance elements as a backup. But I don't want to use them if I don't have to, because remember, it's more expensive. So I try to avoid that. But the cool thing about having those resistance elements in the tank is that it can be approved now based on the environmental health guidelines, because it's basically a resistance tank. If I just look at it that way, I can approve it based on the resistive elements in the tank and not really think about the heat pump, right? So it's kind of a cool trick that we can use right now today. Now, once again, because refrigeration systems move heat instead of generating heat, there's more work output than work input, and that ratio is the coefficient of performance. And let's just look at that on a spec sheet, right? Here we've got, and this is a real spec sheet, and I think you're going to see this multiple times today, probably in examples. And there's my coefficient of performance rated in the lab for this particular piece of equipment. It's about 4.3, okay? And I say rated in the lab because, as you will learn, the lab and the field are different, but still I'm putting a 1 unit of energy in. I'm essentially getting 4 units of useful work into the hot water, right? And we're rating this off of horsepower. So it's about 2.8 kW. So if I were to look at the spec sheet, it's like 2.8 kW, but I'm getting 12 kW worth of work out of it. That's what we're talking about when we're talking coefficient of performance, right? So it's basically just a ratio, work out to work in. So let's go and compare these once again, just kind of from a usefulness standpoint. Resistance, I put 1 unit of energy in. I get 1 unit of energy into the water. With my heat pump water heater, I put, this is another example. I put 3 kW in and I'm still getting 12 kW out. So I kind of said that in a way that was not completely clear. I put 12 kW in, I get 12 kW into the water. With my heat pump, I put 3 in, I get 12 out, okay? So hence the energy effectiveness of the heat pump water heater and why that's our future technology. But we have to figure out how to match the system to it, okay? So the hot water system must be properly designed to accommodate that difference between the generation times. I'm getting fast water heating out of my resistance. I'm getting slower water heating out of my heat pump water heater. That's one reason why the hybrid is kind of cool. And once again, we'll talk about the hybrids today because I got to back up. And in my own house, that's what I have. You know, for residential use, it's a completely different world, but still, I have a hybrid heat pump water heater. I run it off the heat pump as much as possible, but when Christmas comes and all my family's there, I've got the resistance elements as the backup as we really draw down on that tank. So it's a really nice mix of technologies. So here's our environmental health challenge. Once again, resistance only should be avoided because it's just expensive, right? And food service is such a hard business and such narrow margins that if we just force people to go with resistance, we'll crush them. They'll just go out of business, and then you won't have your favorite restaurant down the street. And that, I don't know about you, but that breaks my heart. And the 2020 environmental health guidelines do not require do not allow approval of the heat pump water heaters because the current guidelines only address input and not actual heat output, right? So the current guidelines are saying, I need you to mix a certain amount of water, and I'm going to base your ability to do that off of the spec sheet, and the spec sheet input is what I'm looking at. But the hybrids do have these resistance elements. So as I said, we can use that to our advantage, right? There's a path to permitting. So let's now get to Barry's cool technical doc and how to use that, right? So there's really only 3 steps to approve a heat pump water heater using these current environmental health guidelines. Now, once again, if you get into a project, and as Amin's going to mention, you're going to find that there are some limitations, but we can drop these units into current existing facilities if the facility is not that big, okay? So here's the 3 steps. The first, most important one, and I got stars on it because Amin's going to talk a lot about this. This is his first big project, is to figure out how to update the codes for the gallons per hour requirement. But first thing is, how much hot water am I going to need based on the numbers of sinks and dish machines, etc.? And there's a couple of ways to look at that, right? And this is in that CCDEH sizing requirements for storage water heaters guidelines. So first thing, how much water do I need? Second thing, I'm going to go out to those guidelines and use either Formula 2 for the electric water heaters or an Appendix 3 sizing table for the same water heaters to see how much energy, how many kW I need to meet that gallon per hour requirement. So how much water do I need? How big does my system have to be? Then I'm going to compare the system that I'm planning to install to the one that the guidelines tell me I need. And if my system is equal to or better than my requirements from the guidelines, then I'm golden, right? If my system's underneath, then I got to figure out some way to either drop the hot water requirements or make my system better. But this is all doable right now today. So easiest, most fun thing to do, of course, is to use an appendix. The appendix in the guidelines is really simple. You know, let's say I need, let's go down here. I need 34 gallons per hour at a 70-degree temperature rise, and so I need a 6 kW input, right? It's that simple to use. That's why I love the table. But you'll notice that the table is even numbers, you know, 1, 2, 3, 4, or whole numbers. I'm sorry, whole numbers. 1, 2, 3, 4, 5, 6. There's no fractions. There's no, you can interpolate if you want, but use the table if it makes sense. But if you have something that's in between, like, a 1.5, then you're going to want to use this Formula 2, which is equally easy to use, So let's step through a couple of examples real quick here. Keep an eye on my time. So example number 1, I got a cafe. It requires 50 gallons per hour of 120-degree water at a 70-degree temperature rise, okay? So, you know, not too bad. We're following our steps here. So that's step one. I need 50 gallons per hour. Step two, I go to the table. And you can see here 70 degrees, 52 gallons per hour. Yeah, I need 9 kW of input into my electric water heater. Okay. So really simple stuff. I could use the Formula 2 as well. And in Formula 2, you can see my requirement is 8.7 gallons. But the 9's going to work out because when I get to my spec sheet here, in my spec sheet, I actually have 12 kW worth of input. So 12 is bigger than 9. I'm golden. I can put that unit in and that'll work fine. But just keep in mind, this is also a cafe, right? So that's my qualification for all of this. Is it scalable up to a certain point, but this is not a Cheesecake Factory. This is a smaller water use. 52 gallons per hour is relatively small for most commercial food service applications, okay? And you know, if I'm looking at my spec sheet here, the spec sheet for this particular unit is listed at both 240 and 208. But even at 208, I'm still 9 kW, right? So my unit even listed at 208 would be fine. But here is an interesting, I won't call it a loophole, I'll call it a judgment that we got clarified. Barry went out and asked the environmental health folks about this. And so the CCDEH guidelines do not require voltage correction. You know, initially Barry was writing the SF technical bulletin and trying to figure out all of the voltage and how do we make this stuff work. And come to find out, it's not in the guidelines. And so you can use the 240 you can use the 240 volt rating if you don't see a 208 volt rating. The 240 is fine. You can assume that, right? So if I had if I go back to my cafe and I needed 11 kW, I've got 12 kW at 240 right here. That will work. Okay, that works okay based on our judgment calls. And here's why that works. Because in reality, the heat pump's going to do most of the work, right? And the resistance elements are the backup. But remember, we're qualifying the entire install based on the backup. So the heat pump water heater install, you know, approved on the resistance elements will be conservatively sized. So that's why we don't get too worked up about that stuff. And I do want to say, you know, stick with this, you know, continue with what Amin's going to say, and then stick around for Noah's bit, because you're going to learn a lot more about what we're finding in the field in the real world compared to all of this as well, how these units are performing. So now let's get to a second. This is a little ice cream shop, so it's even smaller. And in this one, I'm looking at 25 gallons per hour of required hot water. And I run the Formula 2, and that's 4.4 kW, which is an in-between, right? That's not a 4 or a 5. And if I look at my spec sheet, this particular unit I'm going to use has 4.5 kW. So this is one where if I actually tried to use that appendix, I'd be screwing myself. I'd go in there and it would tell me I need 5 kW, and I'd think that the project wasn't going to fly. But as soon as I use the formula and get, you know, a little tighter number there, then I realize that my spec sheet's okay, my equipment will work in this application. So that's just the little subtleties of when you use the appendix and when you use the formula. Neither one is hard to use, so it just gives you an idea, though, a little subtle bit. So here's an important thing. Efficient design is a cost-effective solution when the gallons per hour requirement and those kW requirements exceed the kW rating of your heat pump water heater. So let's say I've got a situation, I use my formula or the appendix, and I need 14 kW input, but I know that the heat pump water heater that I'm looking at, it's only got 12 kW off the spec sheet. I'm 2 over. What do I do? Well, that's when I start looking at the system itself, you know, and what are some things I can do? The primary biggest thing, and an act that's just a design process is just becoming more and more normalized, is to use a heat recovery dish machine and just put that on the cold water line. The heat recovery dish machines are so good at recovering heat after these, a few run cycles, that they do not need to be connected to a hot water line. They have their own booster heaters. And so that just takes that load, a major load, off of your centralized water heating, which would, essentially remove that load off your heat pump water heater. So let's say I take 3 kW off the heat pump water heater. Now my heat pump water heater spec matches the gallon per hour. Everything is cool, right? And the other thing, where allowed by environmental health, if you can do distributed water heating at hand sinks and things like that using point of use heaters, that's another way to take load off, right? And here's just an example of the way that, and actually this was one of Amin's projects where he took a restaurant water system completely apart and put it all back together. And it's in the traditional system, there's a gigantic loop with all of these loads on it that runs around the entire facility. You get a lot of heat loss, you got a lot of inefficiency. And it means that all of these loads are all on the water heater, okay? But what you can do is you can remove a lot of that load, like here's our heat recovery dish machine. See, now I've taken that load off of the centralized water heater. And in this example, also all of our hand sinks out here, restroom sinks, we've removed those off the central water heater by using point of use. And so then what I end up with is my central water tank, and what it's feeding now is my pre-rinse valve, 3-compartment sink, mop sink, some of those heavier loads that need to be on there. So that's another way to use design so that you can actually qualify a heat pump water heater install in commercial food service. And then Amin's going to talk about this as well. You can, the guidelines do allow you to use more than one heat pump water heater in a facility, but there are some, it's just going to be natural space and airflow restrictions on that kind of stuff, right? And here's a picture of Michael Slater, who's a researcher now at over at PG&E in their lab. And we were at a restaurant show, and I asked him to stand up, next to the unit, just to give you an idea. They're larger than resistance, not ridiculously bigger, but they're a little bit bigger. And these units need air circulation. They are refrigeration units, right? And they will cool the space. So always keep in mind that you will, siting is not going to be the same as for a heat pump water heater. It's not going to be the same as siting for a gas water heater or electric resistance water heater. And this is a perfect example. These are multiple heat pump water heaters in a grocery store. You see a lot of air circulation around them. You've got a space. It's probably going to be a mechanical room that's warmer. So as that space cools down, it's not going to, turn the thing into a walk-in box, right? So in summary, current and pending regulations will mandate electric water heating. This is coming, right? Heat pump water heaters can be approved using current environmental health guidelines. The SF Environmental Technical Bulletin, it was created as a really useful guide. Hats off to those guys. Effective and efficient plumbing design can make heat pump water heater approval easier and more cost effective in some situations. And refer to that California Energy Wise design guide just to get more information on that. And there are installation requirements for heat pump water heaters that need to be considered. I can't stack 4 of them in a tiny sealed up space. That doesn't work, right? I'm going to ask a favor of you. If you will just pull out your phone, and this is a Survey Monkey, and just give us a little feedback on this class. This class today is part of the Pacific Gas and Electric Workforce Education and Training Program, and we do like to get some survey information back from you. So if you'll do that for me, and also tell us, what are the classes you want and what other subjects you want us to do related to water heating. There's a lot of information we all have. We build these classes for you. And with that, I'm going to say thanks, and I'm going to stop sharing and turn it over to Amin, who's got loads of killer information. So thank you all for listening today.
Thanks so much, Richard. There was a lot of questions being asked. If you have a moment and would like to
Yeah.
answer any of those right now, that would be great. And then also, everyone, there'll be a little bit of time at the end where we'll try to talk with you more about the questions that we see being asked. That would be good to share with the whole group. And with that, over to you, Amin.
Awesome. Thank you. Thank you, Richard, for really kicking this off. And I'm really excited to kind of continue on this topic. We're going to be talking about heat pump water heater 102 and really looking at the water heating sizing guideline revisions and getting deeper into this conversation. And so let me, a little bit about the agenda for today. We are going to be looking at some intro and some background into this work, some of the early motivations, and then go into kind of the heat pump water heater 202, and just really look into some of these configurations. And later on, after we kind of have that really good background, we'll get into how the health department does sizing and the changes that we are making to the sizing guidelines. We'll cover a sizing exercise or some examples actually. And, as we kind of add some complexity to the sizing guidelines by incorporating heat pumps, we're also simplifying it by adding a kind of like a spreadsheet or online sizing calculator to kind of do most of the work for you. And so ultimately, we'll discuss kind of what's coming up in phase 2 and, what's going to be the next steps. So really look forward to kind of, getting into this. I want to kind of recognize some of our funders and collaborators. This project started with 2050 partners and Mai Gantley, and this was a CalNext project, really looked at overcoming these barriers to electrification of food service hot water in California. And we worked closely with Frontier Energy on this project. It actually involved doing 4 monitoring at 3 field sites to get some data and disaggregate usage in facilities. And it also involved really working with the health departments as well and other collaborators. So we'd like to really, that was the original project funder, CalNext. And then after that project completed, we got some support from PG&E's Code Readiness Program and our current funder as we do more advocacy this year and continue to update and graduate these draft guidelines to final guidelines and also really develop the calculator from just an idea to reality. So in doing this work, working with some great folks in the community. Frank O'Sullivan has been doing training of hot water systems with the health department for decades, and he's providing great oversight on all this. Richard Young and others at the Frontier Energy are doing top-notch work, and we're also working with Barry Hooper and Nick Kastner at SF Environment. And to round things off, we have a great environmental health roundtable. Great folks that are really helping us kind of in both Southern and Northern California. So it's been really exciting to continue the conversation with them. And yeah, so this has been going on for over 20 years. We have a history of collaboration. We started with doing a lot of training of the health departments. And later on, we actually were able to help them develop their sizing guidelines. This was maybe a decade ago. We worked with updating their tankless guidelines to essentially previously they were just sizing based on gallons per hour and using, say, the gallons per hour requirement of dish machines. But in reality, when a dishwasher is used, it's using all its hot water in the rinse cycle in 5 to 15 seconds. So we're able to help them update those guidelines to make sure we size tankless units properly. And in essence, one tankless unit would just cover the dish machine. And so you would need additional units to cover the rest of the facility. So that was some early work, and we were able to develop some trust and kind of really get ready for this effort, which was, this effort started in 2021. I was working in the laboratory doing testing on heat pump water heaters, and I realized, wow, this is really great technology. A lot of work was being done with multifamily buildings, either lab or field testing. And that's kind of when I realized, oh, we need to find a way to get heat pumps into the food service facilities. And so we started the conversation there. But I think it took about a year or two until we really got going. We have, facilities and design firms that were trying to put in heat pump water heaters in restaurants, and they were getting rejected by the health departments. And so through the Bay Area Decarb Coalition, we started a conversation, and that just kind of snowballed from there. It really got us going. We were able to get some projects funded through CalNext, and we were able to get into restaurants. One was a mixing valve study where we got to add a mixing valve to the system, to a gas system in a restaurant, but it gave us the opportunity to kind of get in there. We also did a market potential study on heat pump assisted hot water systems. So if you're not in a position to change your system, or if the health department doesn't allow you to, you can still add heat pumps. And so we'll talk a little bit more about that configuration later, as well as working with Frontier Energy. We were able to update the design guide, which is on its 3rd edition, to incorporate heat pumps sizing, as well as a lot of advanced optimizations like pump controls into the design guide. And so, yeah, here's some resources where you can download these reports. And so kind of moving on, kind of coming back to where this project started. This was the CalNext project. And our original objectives were to characterize hot water demand and equipment consumption through field data collection. We won't be talking much more about that today, except that phase 2 is going to really look at kind of disaggregating that data and really utilizing the research that's out there. And so, yeah, we'll come back maybe towards the end for that. We engaged mainly with key stakeholders, including environmental health leaders. And, ultimately, we presented some field data and some different sizing approaches, and, really worked up kind of like a draft of the sizing guidelines. And that's kind of where this project ended. And currently, the PG&E Code Readiness Program is now funding the next phase of this work and collaboration. So before we get into that, some of the reasons, kind of the motivations, some of the other motivations outside of we can't put these in restaurants, were that we have new rules that are going to be in place in Southern California, as well as in the Bay Area, that for different size heat pump or different size water heaters, for example, in the Bay Area, anything below 75,000 BTUs, there's a mandate that you need to put in 0 NOx water heaters, essentially saying you have to put in electric water heaters starting in January of 2027. And in Southern California, with new buildings or major alterations, it actually starts earlier in January 2026 for larger size water heaters, right? So that are, what you typically put into food service facilities. So yeah, it's coming. The rules are coming right away. This impacts roughly 60% of Californians. It's 2 air quality districts, but 10% of the total area, but a huge portion of the restaurants would be impacted. So why does this matter? As we mentioned, there's no current path for heat pump water heaters in restaurants. I'm speaking to all types of heat pump water heaters. Also, we can't really afford to put in resistance in restaurants. It costs roughly 5.5 times more in California to heat water with resistance than it does with gas. And also we likely don't have the electrical capacity needed to ramp up if we even tried. So A lot of restaurants are close to maxing out their electrical panel capacity, so there's additional charges there. And this could all lead to exemptions for food service, and we don't want that. We want to kind of be able to decarbonize and really have these air quality rules really kind of being the foundation for this change in California. So moving on, right? This just kind of expedites the health department sizing guideline revisions. It expedites the lab and field research. It expedites the education and activities and advocacy work. And finally, we're hoping that it also expedites manufacturers of heat pump water heaters to develop more products that are suited for restaurants. And so some key areas that we like to address, for example,
Excuse me, Amin, are you still showing your slides?
Yes. Oh, is it not showing?
They may have dropped. I don't see them anymore. Shannon, do you see them?
Susan, I do see them. It looks
Oh,
good on my
okay.
end.
Yes,
Yeah.
they're fine.
Okay, thank you. Sorry, it's just my system. I'll figure it out.
Okay, great. Yeah, so yeah, ultimately, some restaurants can be greasy, we have a way to protect the evaporative inlets, and so they don't get fouled up from grease or other debris. And so there's some additional kind of heat pump specific requirements. Another one could be having ability to duct that cool air and that dehumidified air from heat pumps to where we need it most in restaurants, which would be to cool the cook line or dehumidify the dish room, for example. So just something to put out there. Let me advance. So just, as we look at what's suitable, let's start looking at some of these unitary heat pump electric resistance water heaters we call hybrid water heaters. And if you operate one of these units, these are light commercial units in hybrid mode. Typically, one of these units will displace a small gas water heater that you would have in a cafe. And these are just examples. They're just rules of thumb. Rules of thumb. Different facilities will require more or less. So in quick service, likely 2 units operating hybrid mode, which means it's operating the heat pump and electric resistance as needed, will be suitable for quick service, most quick service restaurants. As we get into trying to operate these units in efficiency mode at a higher COP, likely you'll need a 3rd unit to be able to meet the peak loads in that facility. As we go to full service, you start basically with 3 units in hybrid mode, and that kind of meets the needs of full service facilities. Another alternative to integrated units is split systems. And here's an example of, you probably would likely need 4+ units plus a couple storage tanks to meet the load in a full service facility. So the scale, what I'm trying to show here is that you're typically displacing 1 unit with multiple indoor units or multiple outdoor units, essentially. So it does take extra space. And, Richard really covered this in more depth. I just wanted to kind of share kind of the applications of integrated units. They work really well in smaller hot water loads and small facilities, but they struggle with large hot water draws in large facilities, mainly because typically you don't have the proper ventilation in restaurants to add several of these units in the back of the house. And also they do struggle with that warm return water temperature, and trying to figure out during peak times, but as well as during off-peak times, really how to operate that unit in a way that is efficient. There are moments where if you're not operating it for many hours through the night, that you can destratify that water. And if you need hot water quickly, you may not have that storage. So that's kind of one of those examples. And that's why the bulletin has been structured in a way to kind of focus it on more simple systems. Yeah, and so as we go to split systems, it starts to get a little bit more complicated. This is an example of a split system that is a single pass unit. You have the hot water going from the top of going from the heat pump to the top of the tank. And it essentially, this is kind of like the design that it would be utilized in many restaurants, especially the larger restaurants. Yeah, this is, as we were talking about the heat pump assist, this is a diagram from that study. This shows kind of the primary system, which is the primary heat pumps and the primary storage tank, being down or upstream of the existing water heater. And this could be your existing gas water heater. And so your existing gas water can be like the temperature maintenance tank. Its role could be to maintain the recirculation supply temperature in your system. During the day, it's going to get an assist from the primary hot water system that's going to put hotter water into the temperature maintenance tank. And the set point for the gas water heater or the resistance heater used in that area would be a lower set point. So in a sense, it wouldn't really be operating during the day much, but at nighttime, it provides the support of being able to maintain that recirculation supply temperature. So this is a very good application of like retrofits where maybe you can't put a full size heat pump in there, but we can still decarbonize and electrify it partially by adding heat pumps. And regardless of where you are, if your health departments haven't yet updated the sizing guidelines, you can come in with a system such as this. Another configuration is these integrated units can be plumbed with a recirculation system. And so this is an example of how they would be. We are testing these units in the laboratory in this configuration. And essentially you want to have these integrated units be in parallel. And so therefore they're balanced, so they can balance the hot water loads from the draws, as well as they can balance that recirculation return water coming back. So one unit is not going to be fighting the other unit. One unit's not going to be like hanging out while the other unit's like maxed out and running lots of resistance and trying to keep up. So just to differentiate between the split systems, this is what we saw earlier was commonly known in the industry as a swing tank system, where the electric resistance storage water here is downstream in series. What we see in food service is really a significant use of return to primary systems, where that one storage tank or multiple storage tanks can handle that return water. You don't need a swing tank or a supplemental tank for just a temperature maintenance system. And this allows for actually higher efficiencies and less complexity and less footprint as well. And so this is an example of a single pass system where hot water is reaching the top of the tank. There's also a multi-pass system where you're recirculating in much higher flow rates, but at a lower temperature drop, similar to gas boiler systems. And that's kind of, you're sending that water to the middle of the tank. And so those are the two types of split heat pump systems with return to primary configuration. And moving from that, this is just kind of provides kind of like a menu of different types of water heaters that are on the market that are suitable for restaurants. If you have a really small like chocolate shop or like really small facility, you can probably get by with like one of these Rheem residential any manufacturer residential heat pump water heater. As you work up to cafe and quick service, you can work with these light commercial integrated units. Typically, these units utilize R134A, and they can work down to 35 degrees. Keep in mind that if you're operating in hybrid mode, especially with these light commercial units, the cutout temperature is more like 45 or 47 degrees. So you're operating, if that space gets cold, you're operating just using the electric resistance until that space warms up and the heat pump can activate. So yeah, that's something to keep in mind. Now, CO2, there's some great technologies out there, either modular and small, these Sanco 2 units, or larger with, there's a number of manufacturers that make these larger units, and there's going to be more manufacturers that are going to be making these modular units. So there's a lot going on there with CO2. And with the conventional refrigerants, we typically have 134A or 513A, and we're transitioning to kind of 513A and 454B. And as we transition over, we can handle lower ambient temperatures. Currently, a lot of the units in the market can handle 40-degree ambient, and you need electric resistance backup. But we're going to get to a place where in most climate zones, we can use conventional refrigerants to handle, ambient temperatures in 10 to 23-degree range. So it's just, we're getting lots more tools in the toolbox to kind of support food service, and that's really exciting. Nonetheless, there's significant barriers, high first costs. There's still a significant lack of familiarity with this technology, with operators and health departments and many other stakeholders. There's some technical barriers. There's certainly more complexity. There is space and ventilation constraints, electrical infrastructure constraints, especially in existing buildings. There are some noise, and they are getting quieter, so that's kind of getting better. And there's also installation challenges. As we mentioned, it's not always a one-for-one replacement. And currently we're starting to get through the regulatory barrier. That's the one I'll be focusing on in the slides coming up. And so, currently in the current California Retail Food Code, there's no place for heat pumps. Certain municipalities are starting to allow them. In some cases, it requires monitoring so they can see that the unit is holding temperature. In other cases, like these integrated units, they're allowing them as an option as well. So what the guidelines currently, they currently don't really support heat pump water heater technology. The reason is that if you apply the electric resistance formula that they use for calculating the kW input, that formula for thermal efficiency uses a fixed value of 0.98 for electric resistance heaters. Currently, there's not an option to change that value to represent the COP of heat pumps. So that's one key piece that we're working on. We also want to acknowledge that there is an additional heat loss load from the recirculation system. Currently in the guidelines, it does not factor in recirc losses as a load onto the water heater. And, additionally, obviously, ambient temperatures and recirculation can impact the efficiency of the water heater. And that's something else we also want to incorporate as well. One big thing that's an issue is that the current sizing guidelines and the ones we're proposing will not be factoring in the storage tank capacity as part of meeting the hot water load or the peak hot water draw of the facility. The reason is we're making so many changes. That is one that we'll have to kind of consider as part of phase 2 or phase 3, come back to that. So in some ways, we're starting to reduce when heat pumps are allowed, we'll have right-size them as much as possible. But really, to truly right-size heat pump water heaters, we'll have to factor in the storage tank volume. So we'll talk a little bit more on that. And also, we need a path for hybrid or dual fuel systems. So in a sense, calculating the kW input for gas and electric water heaters. So phase 1, the draft sizing guidelines have been completed. We're working to finalize those. And generally, what the sizing guidelines currently were doing, where they were oversizing the hot water demand, and they were undersizing, but in some ways they're also undersizing the like legacy or conventional dish machines. Typically, those dish machines run at higher real world hot water volume per rack, and so there was kind of like a balance there. The current guidelines were also undersizing for the winter cold water supply and for the heater outlet temperatures. So that's something that we addressed in the guidelines. And they were undersizing for heat pumps when calculating the for the efficiency value, right? So our goal is to kind of right size for all these parameters, but still use the methodology that's been applied and with health departments, not just in California, but nationally. And so that's kind of the breakdown of where we're going. Ultimately, when we do achieve right sizing, it's going to be a holistic approach, and the goals are going to be to optimize the storage tank volume and minimize recirculation loads, and therefore decrease the number of heat pumps. In doing so, we'll lower that first cost, we'll reduce the electrical requirements, and also ultimately lower the operating costs for the facility. Yeah, and so what specific draft updates did we make? And so this is just a sample page of the sizing guidelines. I think it's roughly like 20 pages currently, or 15 pages. We probably added another 10 or 15 pages on top of this. And we added extra formulas for heat pumps. In fact, we added 4 new formulas just focused on heat pumps. And we are also going to look at, like, our goal is, for this phase of the project was not to do a full overhaul. And as mentioned before, we're excluding storage tank capacity. So kind of moving on, we had to add a bunch of new appendices to kind of to ensure that we have the right information and lookup tables that health departments and operators could use. And therefore, here's an example of the indoor heat pump COP for with and without recirculation. And it's showing you a bunch of different configurations. For example, single pass primary, multi-pass primary, and that's with a swing tank or electric resistance in series, as well as there is single pass and multi-pass primary return to primary options. And there's an option for if your system has recirculation or if it does not. If it has recirculation, typically those COP values are less, since we're factoring in real world heat losses. And hybrid water heaters are also incorporated here as well. So this particular appendix is Appendix 7. As you can see, there's a number of appendices relating to the COP of heat pumps, but we also have earlier appendices that deal with the set points in different types of facilities, the outlet temperature, as well as Appendix 4 deals with the winter design day cold water and cold air supply temperatures. And so there is a by zip code or by climate zone, you can reference the proper ambient condition for your facility. So that's a lot of information. We do have a sizing example that we will cover quickly. And this really, the goal of this is to get familiarity with the new sizing guidelines for integrated and split heat pump water heaters, and start working with some of these appendices. It is recommended that in the future, when the calculator is available, that that be utilized as the primary way of sizing for food service. Of course, you can reference these sizing guidelines just to kind of get that background as well. So in this example, we're going to be looking at an indoor installation of split heat pump water heaters in a cafe. In the picture is, a location where you can put a single unit, say above the the ice machine, or it could be above the reach-in refrigerator, any place where there's hot air that we can capture, closer to the false ceiling. There's a lot of hot air in the back of these cafes, and it's a great place to capture that air and maximize the COP of the heat pump. So in terms of sizing, this coffee shop is compact with less than 60 feet of piping. Therefore, it's not required that you need a recirculation pump and return system. And this coffee shop does use a single service eating and drinking utensils. Therefore, when you're sizing for the total gallons per hour hot water demand, you can actually size down. There's a reduction factor that can be utilized there. So there's 3 tasks. First, we size for the hot water demand based on all the hot water using equipment. Essentially, the health department assumes that all end uses are on at the same time, and that's how they size for hot water demand. Task B is calculating the kW input for both an indoor and an outdoor option with these split systems. And task C is to quantify the number of heat pumps for each application. So, this is kind of the standard table that the health department uses. They have you put your fixture counts in the first column, and then there is a fixed value typically for the demand per unit. When it comes to dish machines, those values can change. And to simplify this sizing, we're going to assume that the dish machine is a heat pump, is a unit that uses heat recovery. So it actually does not use any hot water. So that kind of reduces the total hot water demand for this facility. So as you do the fixture counts and demand per unit, and you allow for that allowance for single service utensils, you get a minimum recovery rate of 62 gallons per hour for this facility. And as this is kind of how you see that your dishwasher does not require hot water connection. With these heat recovery machines, on the spec sheets, you can see the plumbing connections only ask for cold water. And so that's a great way. Now, so to go further to calculate the kW input, or the second task, we need to know the supply or temperature or the set point of the water heater. And, we have a lookup table, Appendix 3, where for cafes without a recirculation system, the typical set points are 130 degrees. And we can also go to, the second step in task B is to look up the winter design day cold water supply temperature, which here in Oakland, where we're doing this example, it's 52 degrees. So we now know the temperature rise, which is 78 degrees in this example for this facility. We can also look at the specs of the heat pump. What we see is that it's going to deliver 150 degree water, and it's going to use a mixing valve to temper it down to 120. And that's what's recommended for this application. So as we move forward with this, the next lookup table is to look at the heat pump COP. We can go to Appendix 7 here. And for cafes, we see the COP is 4.5 at 130 degree set point. And based off of that, we can now do the calculation for kW input, which comes out to a minimum input of 2.6 kW. And if we were going to do this outdoors, it's a lower COP, we would need 3 kW of input. So that's kind of the calculations. In the real world, like as you do it, either for the indoor or outdoor application, because the health department sizes for the kW input instead of the kW output, regardless if the ambient temperatures are lower outside, and with this unit, because it fixes the output capacity, it just increases the input kW when you're operating this unit. Either way, you're going to get three units, which 3 outdoor units or 3 heat pumps that would be needed to satisfy this cafe per the sizing guidelines that we're revising for the health department. So yeah, sorry, I kind of went that through fast. There are some slides there that kind of detail the capacity of this, the heating capacity of this unit, and as you can see in the blue line above, between 5 degrees and 86 degrees, the output capacity is fixed with this unit. So if we're going to do this example with integrated unit, we'd follow the same procedure as we talked about earlier. The spec sheet provides a lot of information that we can utilize to for our lookup tables. In this example, yeah, so we can go from there. We know that since this unit is operating at 208 volts, this unit utilizes 9 kW of resistance instead of 12. And so that is something that we'll utilize in our calculation as well. Yeah, the procedure is very similar. You can see here that you can go to the lookup table. You can go to the lookup table and look up 134A for a hybrid unit, and you can see for a cafe, you see a COP, a daily COP of 2.7. That's one of the key pieces to take from this, as well as you can look up the spec sheet and you can see that there's a recovery rate in gallons per hour. And just be mindful that the kW output when operating at 208 volts is less. You don't have that 12 kW, you have 9. So the total in hybrid mode is actually 21.2. So just something to keep in mind as you're kind of looking over spec sheets. You can apply the same kW input equation, and you get a total kW input requirement of 4.37. As mentioned, these units provide 21.2 kW of output, but the total input is 7.8. Well, let's see, did I get that right? Yeah, the total input is 7.85 kW. So this unit is a little bit oversized, but nonetheless, nominally you'll need one of these units for a cafe. And so that's something to think about. Now, I think I have a little bit of time left. I just wanted to kind of cover a lot of this complexity of lookup tables and equations we try to tackle with this CCDH spreadsheet, and it's kind of doing the sizing, doing the calculator is doing the sizing for you. So the number of input rates or inputs are significantly less. For example, you'll need your zip code and your facility type, and then you'll need your end use equipment information, and then some information about your water heater and your distribution system. And from there, it'll auto-populate many of the sizing parameters. And by using the spreadsheet, you're minimizing errors, and it's already going to do the recovery rate calculation as well as your water heating input. So this can be used not just for heat pumps, it can be used for gas storage and tankless units, and electric resistance storage and tankless units, and electric heat pumps. And in the future, we can incorporate future tankless units or storage heater technologies. The plan currently is to embed this sizing calculator onto the CCDH website. This is a good site for environmental health staff to access this calculator, as well as it would be a public resource for all operators. And it could be hosted alongside the sizing guidelines that could be used as a reference manual. So to go into it really quickly, the cells that you have to fill out are as in yellow, the calculated cells are in blue, and the values that are referencing another table are in purple. And off the main screen, you provide some information for your restaurant and choose the type of water heater And it advances to the next screen where you provide, it has a table of end use equipment. We'll use drop-down menus to help the user populate all their hot water using appliances and to calculate ultimately the total recovery rate that's needed. And from there, we can now gain information on the heating plant and the distribution system. So it will auto-populate some of the information here. And it provides you, do you have a recirculation system? Is this a full service facility? What's your supply temperatures? Will auto-populate I guess the ambient temperature and also the water temperature and the ambient air temperatures into this. And based on your heat pump water heater options, like if you're doing a split heat pump water heater, if you have resistance backup, where the location of that heat pump is, and the type of refrigerant, from there it can go to the right lookup table and ultimately calculate you a heater COP from that. So this is just in the concept transition to the development phase, but I want to kind of share some slides that we had. Ultimately, you'll be able to calculate the KW input requirements, and it'd be nice in the future to work towards something where you could utilize information about the heat pumps that are on the market to actually size the number of units. But at minimum, we'll get to this level with a working calculator. And ultimately, as we finish with the calculator, part of a concurrent project we have is to really right size for hot water demand. And we're going to be mining all the recent field findings and all the great research that Frontier Energy has done over the last few decades to disaggregate specifically for dish machines and pre-rinse spray valves. Those are key areas that we want to right size the hot water demand, but we might get into other sinks and equipment in the kitchen as well. So in doing so, we hope to reduce the hot water demand requirements in phase 2 of working with the health department on updating these guidelines. And just to give you a quick peek, this is research that was done under this project, this CalNext project. If you look at site 1 and site 3, those are 2 sites where the real world hot water demand from is less than the calculated demand. And additionally, those dish machines were running over specification, but nonetheless, they're a much larger portion of the total peak demand, anywhere from 40% to 80%. In your peak hour operating in this facility, the dish machine is using the majority of that water, right? And so, this questions maybe the overall methodology for the hot water demand. Maybe we don't assume that all sinks and equipment are on at the same time. Perhaps we actually have to put in an oversizing factor for some conventional dish machines, and then try to reduce the assumed usage of, like, say, mop sinks in your peak hour, for example. But we need to really figure out how to kind of right size hot water demand. This is an example of where how we're doing the sizing doesn't really measure up to how the real world usage is happening. And so with that, I think just what's next, we're going to be coordinating with other research teams to really work on those hot water demand values, and going from proof of concept to a working calculator, hopefully this fall. And we'll continue to iterate, get as much feedback as we can to refine the sizing guidelines in the PDF form, as well as the spreadsheet calculator. And hopefully by next, middle of next year, we'll be presenting this to the Environmental Health Association in California, and we will have a working calculator, and we'll be ready to go. So that's kind of the goals for this project. And with that, just want to say thanks. Thanks for hanging in there. I know that was a long, dense presentation. And I will open it up for questions and pass it back to the team.
Great. Thank you so much, Amin. That was so insightful and really interesting. Could you stop sharing, please?
Sure.
Great. And then I'm just going to share my screen because we'll be pausing after this part of our session and then returning after a little time. But yes, let's check out some of the questions that have been asked. Richard's been doing a great job in responding to a lot of questions. But I see, I mean, that you are interested in answering the question about the progress on wastewater heat recovery. Is there anything more you'd like to say about that?
Yeah, regarding wastewater heat recovery, certainly some manufacturers have integrated wastewater heat recovery. The majority of manufacturers have integrated exhaust air heat recovery. And some, European manufacturers actually incorporate both. Nonetheless, typically they're used for maintaining the tank temperature of the conveyor machines. They're typically not used for, I guess, preheating from cold water supply, the main rinse water, which is potable water. So they're used within the dish machine, just not typically used for the rinse water heating, which, I think one of the advantages of heat recovery is that for some units, you can use just cold water. And you can also be ventless. And part of that is really taking the heat, recovering the heat from the exhaust side, right? So there are advantages to drain water, but there are more advantages to exhaust heat recovery. So long-winded, but I hope that helps.
No, not long-winded at all. I mean, thank you. And then another question here. The multi-pass COPs seem to be slower than single-pass setup COPs, suggesting that the single pass should be preferred unless there's a good reason to go multi-pass. Do you have any thoughts on that comment?
Oh, that's exactly on point. Exactly. Yeah, they're always going to, single pass is always going to be a little bit higher COP since you're drawing on much colder water in the tank. And naturally, as heat exchangers work, you can transfer that heat more efficiently to produce hot water. So yeah, that's exactly right. Multipass is there as it provides more flexibility. It's also very similar to boiler systems, so certain contractors are more comfortable with that. So.
Mm-hmm. Thank you for that. And I noticed a few questions being asked in the chat, so I'll ask a few of those questions that I'm not sure they were answered yet. Someone was asking if it's possible in the commercial kitchen setting to set the heat pump water heater to 140 degrees and use an anti-scald valve to alleviate the recovery rate problem. Could you respond to that question?
Oh, so yeah, just in restaurants that even on spec, like on plans or in the real world, if you're a cafe or quick service, you're typically at like around 135. If you try to get more storage capacity and you set the water heat pump or water heater up to 150 or 160, yeah, you'll need to put a master mixing valve typically there. So you get the extra storage capacity to be ready for your peak hour, but nonetheless only put out the temperature that's needed. And so that's typically a minimum of 145 in a full service, and typically it's around 130 in a quick service or cafe. The health department requires that you get 120 degrees at your hand sink or your utility sink. Sorry, for your hand sink, it's 100 to 108 degrees, and for all other sinks, it's 120 degrees. So that's what the health department requirement is. Typically, operators are operating a little bit higher than that. So the scalding valve is a good way to, or what we say is like it's like a mixing valve, but a downstream mixing valve is a good way to mitigate scalding at those hand sinks. And so we definitely would recommend that for your lavatory sinks as well as your back of the house hand sinks.
Mhm.
And Susan, I'll just add something so in case there's no confusion. Yeah, you want to run your heat pump water heater at a higher temperature, but when you're doing the sizing, the environmental health sizing, the number that they're looking at is not the temperature of the water heater, it's the delivery temperature, which is a kind of what Amin was just talking about, right? So if you're running your water heater at 150 degrees, that's not the temperature rise that you want to use in the environmental health guidelines. You want to, only use the delivery temperature of 120 degrees. So
Mhm.
it can just get confusing on, yeah. One needs to be
Yeah.
big, one needs to be smaller.
Mhm. Yeah, thank you for
Did I say that
elaborating on
right,
that.
Amin? Did that make sense to you? Let's see if that's
If you are planning to use a mixing valve or temper it down, definitely want to use that lower temperature that's leaving the tank. But if you're not using a mixing valve, then whatever you set the set point of the water heater is what is going to be delivered. Sometimes there's manual mixing that happens, but if your dishwasher is taking the majority of the hot water use in your peak hour, you definitely want to use what's leaving the water heater as your set point temperature. So
yeah.
All right, thank you for that. And then we're just a minute past time, but I wanted to make sure that we understood where we could find that calculator. I think I'm going to be able to link to that from our resources page on the heat pump water heater day resources. And is it available right now on the CCDEH website, or is that coming?
it's all coming, Susan. We will work to finalize the calculator and the sizing guidelines. If the health department would like to post that in advance as a draft copy, so their health department staff and operators can start utilizing it, we'll definitely reach out and provide a link. But currently, we don't have an anticipated date this fall that it will be posted.
Okay, great. We'll be looking for that. I'm excited to make use of that when it's available. And with that, I'd like to say thank you to all of our panelists. Really appreciate your sharing your expertise with us today. Also want to thank all of the attendees for joining us.